right, so this week will actually constitute the very end of our school year. This week and next week I kind of combined into one slightly larger unit because these two concepts overlap so much. There really wasn't much point in splitting them up. So we've got a slightly longer set of notes today than we would have normally had, but I'm going to try and get through them as quickly as I could. All of this is going to follow, obviously, Chapter 16, Section 2. It was the part you should have done your reading note quiz over yesterday. So with that being said, let's jump right on into it and finish off the year talking about light and how it influences what we see in the. So we're all familiar with Roy G. Biv, the visible spectrum that we began talking about a week or 2 weeks ago when we were talking about the Doppler shifts with light, and we talked about how this visible spectrum or any other wavelength of light, visible or invisible, have certain measurable wavelengths or frequencies. What we're going to talk about a little bit more today is how all of this informs what it is we see. So we're going to be specifically focusing not on the invisible light from last week or the week before, but on the visible spectrum and how chemicals and molecules and all of that determine what it is you see. So we typically see this Roy G. Biv thing. Your first experience with it was rainbows from way back when you were a kid and fascinated by them and probably still thought there were pots of gold at the end of it. Why do we see these rainbows is a little bit more difficult a question to answer without getting into stuff we would have normally done throughout the course of the school year. I'm going to summarize it here really quickly. There's this idea that light obviously is a wave. It has wavelengths and frequencies and those sorts of things that you can measure, but it also travels because it can go through the vacuum of space and isn't a vibration. It is its own thing. It is its own particle. We call those particles of vibrating light photons. It doesn't need that medium to travel through because it's its own particle. And so when it enters a new medium, air in the atmosphere of the planet, or the water in the ocean, or the glass in your windows, whenever it enters something new, that slows light down. And that's because there's stuff in the way. I like to think of it as the hallways at school. When we get back in the fall, hopefully, no one knows what's going to happen at this point, but when we get back to school, walking through the hallways during passing period, everything is dead, it's empty, there's no one around. You can go as quickly as you can from one place to the next. The opposite is true during passing period. There's more people in your way. You've got the freshmen with backpacks that are way too large. You've got the group of 12 or 13 people who haven't seen each other in 50 minutes, so they all have to crowd around someone's locker and take up half of the hallway, creating a traffic jam in the other half of the hallway. You've got stuff in your way, and that's going to slow you down. The same thing with light occurs. When that light gets slowed down, it turns out, and this is something we would have talked a lot more about. I can include different videos if you want me to that kind of explain this more, but it's not going to be something I'm going to test on. Different wavelengths of light are influenced by that slowing down or by that stuff getting in their way differently. We'll talk briefly about it here when we talk about sunsets and things like that. But the more energetic light is influenced, the violet, the blue light is influenced in a different way than the less energetic red or orange light would be. And so you're not going to get those things traveling together anymore. They'll disperse, spread out, and that's where you get your little rainbows from. They separate themselves out. Oftentimes it looks like the Pink Floyd Dark Side of the Moon album cover. So this leads to the next question, and this is a serious question. I know it seems pretty stupid because ever since we were in like second or third grade, we've always known what the color of the sun was, because every time you grab a yellow marker, this is exactly what, or at least my second grade teacher always told me. The sun was yellow, and now when I look out at the sun in the morning and in the evening, it looks pretty yellow to me. But even artistically, there are representations of the sun that are not yellow, obviously. You're going to have representations that are going to look a little bit more orange. You might have some reds thrown in there. You're going to have a lot of different varieties of color in that red, orange, yellow spectrum that you could potentially use. So what color is it actually? And this is where things start to get weird. Again, this isn't going to be something you need to know a lot of. Anything that I would expect to be on a test, I made blue. Or anything that's a main idea, I colored blue in terms of the text. So here we go. A breakdown. At sunrise, you're typically going to see a very, very, very orange, reddish sort of sun, right? It's the same sunrise, sunset you guys are all familiar with. Just after sunrise, when it's a little bit higher in the sky, this is where it gets its famous yellow color that everyone has always drawn since you were, I don't know, maybe my daughter's age. It's the color we give her when she wants to draw stars. But at noon, please, 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 for the love of all that is holy, without eye equipment or eye protective equipment, do not look at the sun. It will burn out your retinas if you do it too long or too often. So what color is it when it's all the way up there? It's hard to tell, but you can see here just from these two images, it's going to change color apparently. What color is the sun on Mars? Same star, same object in our solar system, but when all of our rovers on that planet turn back and look at the sunrise on Mars, it's blue. So what's happening? Does the sun just decide to change color, or is it different for every observer? No, not really. What's happening is the sun is emitting a pretty steady, there are solar flares and increases and decreases in solar activity and stuff you'd talk about in astronomy if you take that class next year. But the sun, for the most part, has emitted the same amount of energy, the same quantity of energy, the same kinds of energy for the last several million years, which is really good. Otherwise, we'd all be fried and we wouldn't be here anymore. So because it's consistent, because we have the vast majority of it being that infrared radiation, you've got the full visible spectrum coming through, a little bit of ultraviolet. Why then does it look like it's changing color? That's the question. And the answer to that question actually has absolutely nothing to do with the sun at all. It has everything to do with the Earth's atmosphere, the same thing that makes that rainbow, that slows down the light enough to where it can separate the violet from the blue, from the green, from the yellow. The Dark Side of the Moon album cover from Pink Floyd is a really good example of this too. It's that sunlight, that white light coming into the prism and being dispersed, separated out into the rainbow. The idea is that in the atmosphere we have all of these molecules, and last week we talked about how electrons and light interact, and that's what it comes down to. Certain wavelengths the molecules in the Earth's atmosphere can absorb and hold on to, and everything is totally fine. This is great. Molecules of ozone in the ozone layer do a fantastic job at holding on to ultraviolet radiation. Some of the wavelengths of light are going to be scattered. What that means in terms of physics is that they're absorbed, temporarily held onto, but that new energy level the electrons jump to is unstable. They release them, they let them go. Certain wavelengths of light can pass through all of those molecules completely unaffected, and that's what typically happens with your yellows and greens and reds and oranges. So the planet's atmosphere is interacting with the light that's coming through it. You get a lot of scattering of your violet lights and your blue light up here in the atmosphere, which is why the atmosphere itself looks blue. This is one of the things that chapter 16, section 2 talks about, but then you get all of these other wavelengths of light that make it through the atmosphere, that make it through the ozone layer, that aren't impacted all that much by the atmosphere, or at least the length of atmosphere that stuff is moving through. And so that's why you're able to get those reds and oranges and yellows and greens, and more often than not, that's why the sun looks yellow down here on the surface of the planet, is because that yellow light was able to make it through the Earth's atmosphere relatively unscathed. It's also why the sun looks blue on Mars, as weird as that is to think about, because there's very, 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 very little atmosphere there. So most of the blue light makes it through that atmosphere directly into the camera that we have on those rovers. Now for the next part. Why does it change over the course of the day? Obviously, the atmosphere is absorbing and re-emitting, scattering some of this light that is coming from the sun. But why is it changing? It's got everything to do with the amount of atmosphere that light is traveling through. You'll notice here at noon, if you were to look up with protective equipment, please, you'll notice that the sun is going to have a different color up here because there's less atmosphere for all of that light to travel through. There's less atmosphere for all of that light to be refracted through, is the technical term. And so at a sunset, you'll notice this path, in order for you to observe that wavelength of light, this path of light going through the Earth's atmosphere is significantly longer. And the more atmosphere there is, the more chance there is for there to be an interaction between those violet, blue, yellow, green sort of wavelengths of light. And then when you reach sunset, Right, it's the same star, it's emitting the same output, it doesn't change, there's not a dimmer switch that God or whomever might be hitting causing it to change color. Someone over here on the far side of the planet is going to see, maybe Europe, they're going to see at noon a bright blue sky, and then us over here, they're going to see a red sunset because the length of atmosphere that that photon of light or those waves of light had to travel through significantly longer. The high energy stuff gets scattered first. The less energetic red, orange, yellow light is going to be able to make it through that atmosphere into your eyes. That's what you observe. And so that's why you get that weird sort of effect. And so here you can see the little spectral readouts that scientists have done looking at the sun. You know, you can tell that as the sun sets and as it travels through more and more of the atmosphere, you're going to get less and less and less of this blue light making it all the way through. So why then, or what color then, is the sun actually going to be? In order to find out, you actually need to get outside of the Earth's atmosphere, go to somewhere where there is no interference from the atmosphere at all. And so all you really have to do is a quick Google search of photos of the sun from the International Space Station, and you're going to get several of them. That's not some sort of weird Photoshop thing. It literally is a blinding ball of white light. So why does it make sense? This is what you need to know. The sun is white. Why does it make sense for the sun to be white? Because it is releasing all of the different colors of the visible spectrum, right? Remember from last week, white light is not light that you can't see. It's not ultraviolet. It's not infrared. White light is a combination of all of the wavelengths of light. And so because it's emitting your blues and your greens and your yellows and your reds all simultaneously, you're able to see them. We'll talk about that a little bit more. But that was the idea. Sun is white. It's emitting every wavelength of light that is present. The book talks briefly about plants. I ask a couple of questions about it, but it's nothing too crazy. We're not going to go back to the electron transport chain or any of that from biology. We're literally just going to be talking about why plants look green. Green turns out to be the one wavelength of light that plants do a really bad job of absorbing, right? So this tells you a little graph. It's the relative rate of photosynthesis for each wavelength. You have very high rates of photosynthesis with your blues and violet lights, very high rates of photosynthesis with your reds and oranges, and green, all the way down here, very, very low rate. Chlorophyll does a bad job at absorbing and using green light, which is why that green light is reflected back to your eyes and it makes the plant look green. So color itself, these are things to remember from last week. Wavelength and frequency determine what color is present. It's your whole Roy G. Biv sort of spectrum, which also means black and white, technically, if you want to split hairs about it, are not colors. Black is the absence of photons hitting your eye, basically meaning whatever was painted black or dyed black absorbs all of the photons of visible light that hit it. They don't let any of it go. And white colored objects are going to reflect all of that visible light together. And all of it, basically, it's your eyes being overwhelmed saying, you know, hey, we're getting wavelengths of all kinds here. This must be white. It's the combination, amalgamation of all of them together. So this leads us to this little section is talking about the primary colors of light, and then there's another part to this section that talks about the primary colors of pigment. We're going to start with light, and then we'll get to pigment, which is closer to what you remember from art class. So this first part's going to be a little bit different. In order to make white light, you could do what the sun does and produce the full spectrum Roy G. Biv, every single color. Had we been in the classroom with a really, really, really cheap pair of 3D glasses, I would have had you guys look out the window, blacked out all the other windows, and just open up one window. Have you guys look outside, and you would be able to see that full rainbow spectrum of the entire, you know, Roy G. Biv, all of it. And then I would have shut that window, blacked it out again, flipped on one of the sets of lights in the classroom, and had you look at the lights in the classroom. Turns out you don't actually need every single wavelength of visible light together to make white light. And this isn't because of some weird quirk of physics. This is because of biology. This is because of our eyes. Not something you need to know, but our eyes have three different color detecting cells in the back of them, three different kinds of cones. One that detects red, one that detects green, and the other that detects blue. And so because those are the cells in our eyes that detect different variations of light, turns out those are all we need in order to see white light. And so another thing I would have done with the room blacked out is all these demos with light. I've got these light bulbs at the school. If you want to swing by at some point, I guess during your advisory senior year, I could do this for you if you wanted to in the fall. But here we've got a bulb of the color red. Here is a blue bulb, and then here is a green bulb, all producing red, blue, and green light together. And what I wanted you to notice is that there is a where they overlap, where they line up, where all of those meet together, that little ping pong ball in the middle is white. You can see the red light here, you can see the blue light individually here, you can see the green light individually here, but where they all overlap, you're going to get that white light together. Turns out that's the bare minimum that we as human beings need in order to interpret white light. Again, not pigment. I'm not telling you your art teacher was wrong. These are wavelengths of light, not paint. Now, the book then also gets into secondary colors. And so your secondary colors of light, you can actually see here. This right here is the shadow that is cast by the red light bulb. Basically, it's where the red light was blocked by the ping pong ball. Now, the green light and the blue light, green light and blue light, were not blocked by the ping pong ball. And so green wavelengths of light can reach that region, blue wavelengths of light can reach that region, and where they overlap is where you're going to get that cyan color. You'll notice the same thing with this shadow here. This shadow is being cast by the blue light bulb, and where you have red and green together overlapping, you're going to get yellow as a secondary color, and you're going to get, sorry, not magenta, not green, I started writing a G. You're going to get that magenta color over here where your red light and your blue light were both able to reach, but green was blocked by the ping pong ball. And so those are your secondary colors of light. Again, really counterintuitive. This is probably something you never heard of before, but that's because you were probably always in art class playing with paints and not talking about individual wavelengths of light. This is exactly how your projectors, not plasma screen TVs, but old school rear projection TVs, this is how they always functioned. You had these three primary colors, and different combinations of them would produce different colors of light, and that's the gizmo you're going to be working on this week at some point. Here's a little zoomed in photo so you can see all of it. Again, those are your primary and secondary colors of light. So primary, secondary colors, and then a third category which the book comes up with. I shouldn't say comes up with. It's another vocab term that sometimes confuses people, so I wanted to make it its own individual slide, are our complementary pairs. Primary colors are going to be these guys: your green, your red, you can't see that underline, sorry, and your blue. Let's make this a different color. You're going to have your green, your red, and your blue. Those are your primary colors of light. Your secondary colors are these guys right here, where you've got magenta being made by the combination of blue and red. You've got cyan being made by the combination of green and blue, and you've got yellow being made by the combination of red and green. Those are going to be your secondary colors of light. Complementary pairs, by definition from the textbook, this is also in your reading note quiz, are any two that combine that make white light. Any two colors of light that can combine to make white. So typically you would need all three. You'd need your three primaries in order to make white light. Right here in the middle, if you want to make a pair that makes white light, you need a primary color and the opposite secondary color. So if you had blue and yellow, since yellow is made up of both green and red, then you could make white light and they overlap. The example I give here is cyan and red, because cyan is made up of a mixture of green and blue. When you mix cyan and red together, you technically get all three, and it'll give you that white color light. And so those are your complementary pairs. That's all that part is. It confused some folks how you find out which one is which. Just remember that you need all three at minimum. And if you've got red, the complement to red is going to be the combination of the other two colors that are present or need to be present in order to make white light. This is referred to, and this is another definition or vocab term, this is referred to as mixing color by addition, because the more colors you add, the closer to that white color they're going to become. Addition is mixing wavelengths of light to get to white. The next slide, subtraction, is going to be the exact opposite. So, pigments, paints, dyes, everything that has ever, you've ever gone to Home Depot or Lowe's and picked up a can of paint, or anything from Michael's in the art or craft section, literally to the orange Lincoln Way West t-shirts that you have. There are pigments and dyes inside of those fabrics or paints. They're molecules. Those molecules, like we talked about last week, absorb photons. And when they absorb photons, electrons will jump up to a higher energy level. If it's stable, then you're never going to get that photon back. If it's unstable, then that electron will fall back down and it will be re-emitted in a whatever color it was that hit it, or a different color, whatever's going on there. It gets complicated, but we see colors because those electrons were released from those molecules. So how is it that, as an example, the book uses the plants look green? We're going to walk through the whole process. You don't need to know the whole process. You just need to know the end result. White light containing every color from the sun hits a leaf. Most of those colors are absorbed and actually used in photosynthesis. Your violets and your blues and your reds and your oranges are used quite a bit in photosynthesis. The electrons that absorb green photons are unstable. All right, they jump up to the next energy level, third energy level, fourth energy level, whatever energy level those electrons jump to, it's unstable. It can't hold it, and it's going to let them go. When it lets them go and the electrons fall back to a stable energy level, they re-emit that green photon of light. You see that green photon of light leave the leaf. So things are the colors that they are, not because that's the color that they absorb, but it's because it's the one color that they could not absorb. It's the one color they could not hold on to. That's what gives things their color. Your orange Lincoln Way West t-shirts are only orange because they can't hold on to the orange wavelength of light. My black dresser that I'm staring at right now as I make this video is black because it absorbs every wavelength of light and does not re-emit any, and so my eyes are trying to come up with an explanation as to why there's no light coming from that particular region. This is how all of your paints, pigments, dyes have always worked. When you go to mix them, we just talked about mixing light with different colored light bulbs. Now we're going to talk about mixing paints and dyes. This is a lot closer to your art class. This is referred to, this should have been blue, as mixing by subtraction. That's actually literally the section heading in the textbook. You have one section heading in 16.2 that says mixing by addition, and then another one that says mixing by subtraction. One deals with light, addition deals with light, subtraction deals with your pigments, your paints, your dyes. And so the reason it's called mixing by subtraction, as my daughter is figuring out, is because the more and more and more you mix together, the darker and darker and darker those colors become, until finally you get this black color right here in the middle, right? Addition with light, that's a really ugly looking bee. Addition with light, that's even worse. Oh my goodness. Adds up, addition with light adds up to make white light addition, or sorry, subtraction with pigments. When you mix all of them together, you get a black color. And so you'll notice that anytime you try to mix a ton of markers or anything like that together. This is actually the exact opposite. All right, not only is it dealing with paints and dyes and pigments as opposed to wavelengths of light, but this is just in terms of primary, secondary colors, the exact opposite of the previous slide, mixing by addition. So your primary colors here are magenta, yellow, and cyan. If that seems ridiculous and it seems unlike what you probably heard in some of your art theory classes, I challenge you to go check your printer cartridges out. The ink cartridges on your printers, if it's just the box because you don't want to take apart the printer or you're worried your folks will get mad at you for trying to do so, take a look at the boxes for your ink cartridges, and on the side of the ink cartridges you will see these three colors. You'll see magenta, yellow, cyan, and black all together as the 4 colors that are in your color ink cartridges. Mixing together cyan and magenta will give you blue. Mixing together cyan and yellow will give you green. Mixing together magenta and yellow will give you a red color. And so using those combinations of colors in different proportions and things like that, you're able to get every color that you're going to need. This is a nice little cheat sheet. That's why I gave it a full slide. You don't have to write all of it down, but if you wanted to go into the notes that I'm going to put up on Edmodo and just print this slide as a little cheat sheet for when you're doing the homework or the quiz or the mini test, go for it. That's fine. But this is the main idea. In order for something to look white, it reflects back every wavelength of light that is present. In order for it to look black, it absorbs all of them. If it looks red, that means it absorbed everything but red. If it looks green, it absorbs everything but green. If it looks magenta, it absorbed green and could not hold on to, re-emitted, reflected, scattered, however you want to describe it, red and blue together. When both of those red and blue photons of light hit the back of your eye interprets that as magenta. And that's how you're able to see, or why you see all the different colors that you do. I like this little cheat sheet. I encourage you guys to use it. That's why I dedicated a whole slide to it. More on mixing by subtraction, because there are going to be a couple of questions I'm going to ask about it. There's not going to be a ton of math in this unit. It's going to be more of this color stuff. So you have to remember, for an object to look the color that it looks, that's the one wavelength of light it couldn't hold on to. That was the main idea. So when you're mixing things, the reason they get darker is because there are fewer and fewer things that can be released off that surface the more you mix together. So back to this. I noticed a lot of you guys over the last couple of weeks, as you've been printing things, taking photos of them and submitting them as work, have actually struggled in producing red color in your printer. At least, I don't know, a quarter of you guys are running low on some of this ink. So let's find out what color it is you're looking or running low on, and then you should be able to actually check your printer through your computer and see exactly what color it is that you're running out of. Anyways, so when your printer goes to mix colors together to make red, there are 2 colors that it needs to mix in order to produce that red color. And in order to produce that red color, you've got to think about what each one of these different colors produce. You can find this on the cheat sheet from the previous slide, or use this as your example, write it down somewhere. Again, you could print this one off too and use it as a cheat sheet, that's fine. But for cyan to look the way that it looks on that previous slide, you'll see that it absorbs red, re-emits blue and green. You'll see that magenta absorbs green, re-emits blue and red, and yellow absorbs blue and re-emits red and green. So when you want to produce only red ink, when you want something that only is going to release red, you need to mix together the 2 colors that also re-emit that red color. You'll notice that if you mix your magenta and your yellow colors together, that the green photon of light that yellow would have released is being absorbed by magenta. The blue color of light that is absorbed by yellow can no longer be released by the magenta color, and the only color that both of these 2 pigments can compromise on or agree on not absorbing and re-releasing so that it can be viewed by you is red. And that's how your printer is going to produce that red. So if you have when you go to print out those visible spectrums from the worksheets and previous units and you see a ton of yellow but no red where you should have seen the red, that tells me that you guys are out of magenta. Right? You've obviously got yellow because it's producing yellow, but you're out of the magenta. And so it can't, when it mixes or tries to mix that yellow and magenta together, it's just going to keep releasing both the red and the green because there's nothing there that can absorb the green light. And so that's how all of that's going to wind up working. Again, yellow keeps the blue, magenta keeps the green, and the only one that both of them can agree on is red. That's how this works. That's how your printer works, which is kind of cool because all of you, at least in some form or fashion, are probably using that a lot lately. So you could definitely be able to see this in real life. Here's another little cheat sheet. The text on this didn't look as good, so I didn't include it as its own individual thing. But if you want to take a look at that, go for it. Now, last but not least, we have 5 no, I think it's like 3 concepts, maybe 5 more slides. Other key concepts in terms of light, weird things light does that is really, really, really good to talk about because it helps explain literally the world around you. And that's really all I wanted. I took a lot of the math out for the remainder of the year to try and make this more manageable for you guys at home since we're limited in our contact. And so I just wanted you to kind of be, you know, informed citizens at the very least, so that we don't think windmills cause cancer or 5G is going to harm us. But then also, these are things that you're going to see in your everyday life, and it's sometimes nice to have the answer and not always have to Google it or think that, my wife really loves the Happy Giggles or Hello Giggles, whatever it is, website. And she'll try and make a claim and then cite that as her source, and I just kind of laugh and walk away. So it might help you in weeding out some of those things as well. So other key concepts in light. Light and transparent material. What it means to be transparent, because we're talking about how when light strikes my dresser, it absorbs every wavelength of light, and that's why it looks black. Or when it strikes my walls, it reflects every visible color, and that's why it looks white. Well, how does glass work then? Glass literally plays a massive game of hot potato. And here's a little visual of it down below. It's a photon of light being absorbed. Now, this is not the case. Panes of glass are several thousand, if not millions, of atoms thick. But we've got 3 atoms here just for our visual. A photon of light is going to strike that first atom, that first molecule of silicon dioxide inside the glass that is present. The electrons will jump up to a higher, more excited energy state, but it turns out that energy state is unstable. So the glass has 2 options. That molecule of silicon dioxide could reflect and re-emit that photon of light way off back in the direction it came, which is why you can sometimes see your reflection in a window. Or it could pass that photon of light to the atom next to it. And if it winds up passing, which it more often than not does, remember, it doesn't make a choice. These things happen randomly millions of times a second. And so that photon of light that got passed to the next molecule inside the pane of glass does the same thing. It's a little game of hot potato until that photon of light makes it all the way through the glass. This is what I meant when I said light slows down when it enters a new medium. Glass is obviously much more dense and thicker than the atmosphere of the planet, and so it slows down a lot. This stuff gets in its way. It's got to go from atom to atom to atom through that glass. Now, it starts at 300 million meters per second, which is a mind-bogglingly fast speed. Years ago, I did the math for a couple of students who were curious. It could go from Lincoln Way West to downtown Chicago to the Loop. I want to say it was like 2,200 times in 1 second. It could make the round trip from, Lincoln Way West all the way to Chicago and back. I could do that 2,000 times in 1 second. That's how fast this is. So while it slows down a little bit in glass, considering that's where it starts, it's not enough for us to notice yet again, which is also why we don't notice Doppler shifts in light. It's just so insanely fast. Now, the opposite of transparent is opaque. You are an opaque material. My walls are an opaque material. It doesn't allow light to pass through them, and that's where that light winds up getting reflected. Instead of transmitting light, it either will reflect light or convert it into thermal energy. This is important because this is what our atmosphere does. The sun doesn't just produce visible light. It doesn't just produce visible light and ultraviolet light, to give me a sunburn, because my ancestors apparently hid from the sun. It doesn't just produce visible ultraviolet or infrared. Infrared helps heat the planet. It does produce those 3, but those 3 wavelengths of light are the only 3 that can get through the Earth's atmosphere. The ozone layer in the atmosphere does a really good job of absorbing or reflecting, absorbing microwaves, X-rays, and a lot of the radio waves that are coming from these stars, right? They produce every wavelength that is imaginable in the entire electromagnetic spectrum. Our planet allows in, fortunately for us, you could say it's divine intervention or just random luck. It doesn't matter. Fortunately for us, it only allows in these 3, infrared, ultraviolet, and visible light, and it doesn't, and allow in the other ones. If microwaves got in, we would all eventually turn into a piece of chicken that you left in the microwave for way too long. It got super dried out and cooked. That would be bad. If either of these got into the atmosphere in sufficient quantities, then you'd get cancer and die, and that would also be bad. So fortunately, the ozone layer does a good job at blocking a lot of that stuff, but that's what opaque means. Opaque means it doesn't allow that light in. Shadows should be pretty straightforward. I'm not expecting too much here, but the book does give 2 vocab terms that I wanted to discuss, and then we're going to apply it to something that we actually saw a few nights ago on the night sky, which is really neat. Shadows are formed whenever rays of light cannot reach a certain place. Basically, your shadow cast by the sun on the ground, that photon of light from the sun was generated in nuclear fusion, traveled from the sun all the way to the Earth, 93 million miles. It takes 8 minutes for it to make that trip to the planet, only to be deprived of hitting the ground and allowing a plant to use it for photosynthesis because it bounced off of you and got reflected towards someone or something else, right? But that's what a shadow is. It's where light cannot reach a certain part or a certain place. There are 2 parts of a shadow. There is the umbra and the penumbra, Latin terms, so I apologize that they sound funny. In order to make it easier, I like to think of the umbra, the completely dark part where absolutely no light reaches, as an umbrella. It's like your head and your shoulders in an umbrella. The point of the umbrella is to keep you dry. And so no rain is able to reach that particular part. Whereas the penumbra, the partial shadow, is going to be like your feet and your socks. If there's a really, really bad rainstorm, the umbrella is going to do a good job at keeping your face and your hair nice and dry, but it's not going to do all that good a job for your feet. And so that's the analogy I like to make versus penumbra and umbra. Why is this important? It gets back to eclipses. We actually saw one a few years ago. There was this big old solar eclipse. Mrs. Horn, if you guys know her, went all the way down to Carbondale in order to view it. The region in Carbondale was right here for this particular solar eclipse. The solar eclipse is when the sun gets blocked from us, hence the term solar. So the sun is being blocked by the moon, and there was that complete shadow down there by the Carbondale, Louisville, Kentucky area that they were able to see. This happens a lot over the course of a year. It's just whether or not it happens in a region where we can see it. That was what made that one so special, is that it was close to us. We could go view it. What we would have seen, had it not been super cloudy that day, would have been the penumbra, the partial shadow where part of the sun would have got blacked out from our view. Let me get some black ink here. It would have looked something like this. If I can get a thicker marker, maybe. There we go. It would have looked something like this with a partial eclipse where the moon blocks out part of that sunlight. We weren't really able to see it because it was super cloudy, plus everyone was in school. But that's what the solar eclipse is. The reason I bring it up is because the lunar eclipse is a lot more common, and we actually had a partial lunar eclipse a few nights ago. You might have noticed it. The lunar eclipse is when the moon falls in the shadow of the Earth. It could be in the penumbra or in the umbra. Let me get the red color. It could be falling in the penumbra or it could be falling into the umbra. But you'll notice as the moon travels around in its orbit, it can fall into this partial penumbra shadow where it's going to be slightly obscured and blocked. Some sunlight from the sun can get around the planet and light it, but not a lot. This is actually a really cool little part. Obviously, if it passes into the umbra, it'll disappear completely for a couple of minutes and then reappear and reemerge on the other side. But what you should notice if you watch the next lunar eclipse, or you looked out at this moon the last couple of nights, what you would have noticed is that in the penumbra, the color changes. This is going to be your harvest moons, your blood moons, or any of those other weird orange tinted moons. The reason the moon was orange is because that light leaving the sun passed through part of the Earth's atmosphere, filtering out that violet and that yellow and that blue light, leaving literally just the orange and the red light as the long wavelength light that could make it through the Earth's atmosphere. And that's the only light that's lighting up the moon. And during those eclipses, those partial eclipses, I should say, the moon is going to look orange, 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 and orange. It's going to have those reddish orange colors as it passes through that partial fuzzy shadow. And that's why that exists. It's not, some weird omen that something bad is going to happen like societies have thought for thousands of years. It's not, telling you to rearrange your crystals in a certain way like my younger sister would have thought. It's literally just it's passing through the partial shadow of the planet Earth. That's it. So that was a good one. And then polarization is another good one because this deals a lot with really expensive sunglasses. So it's a good idea to make sure that your sunglasses really are working the way that they should. I've got a video on polarization. It's only a couple minutes long, but it does a much better job of explaining it, simply because he's got better visuals and more time to do it than I have. Light travels, we should know, as a transverse electromagnetic wave. Transverse waves have oscillations that are perpendicular at right angles to the direction the wave is moving. Transverse waves can be oriented in any of the 360 degrees. So they could be up and down, left and right, 45-degree angles in between them, it doesn't matter. And so when these transverse waves leave a light source, leave the sun, they're traveling in all of these different 360-degree possible directions. There's no organization, there's no rhyme or reason. It's completely random what direction they're facing. However, when they hit a particular object, let's say you've got a lot of light hitting the surface of a mountain, like at a ski resort, that's reflecting light to you, or off of a car, then it becomes polarized. And it's only going to be one particular direction. So certain filters can block out how much of that light is passing through them. And so this is what your sunglasses, your polarized lenses do. This is how they're able to cut down on glare that reflected light off of cars, off of wet, rainy streets, or off of the snow-covered mountains becomes polarized in one particular direction. And if you build polarized lenses to block out the direction, the angle that that light became polarized in, all of a sudden you've got significantly less light reaching your eyes. And that's what your polarized lenses do. If you want to check whether or not your lenses are polarized, I did this once and actually saved myself a bunch of money. When I purchased a pair of sunglasses, it was one of those cheap knockoff because don't have a lot of money, not even lens crafters, but one of them like in the mall selling glasses. They were trying to claim that their sunglasses were polarized. I couldn't tell a difference, so popped out the lenses real quick and did this little trick. If you rotate the lenses of your polarized glasses to where they're 90 degrees over top of one another, then you should be able to block every wavelength of light that is leaving them. Let me show you why real quick. The video I'm going to attach to this does a much better job. Let's say the polarizing features, the really close slits that they're going to put inside of these glasses, basically little wires inside of the glass, are all vertically oriented. Basically meaning only light that can squeeze in between those little slits will be able to make it through, so any light that is horizontally polarized on this lens would not be able to make it through. Only vertically polarized light would make it through. And so if both of these lenses from both sets of glasses have vertically polarized lenses, then they're both going to equally let through that vertically polarized light. But if the lenses are at right angles to one another, and this pair of glasses up top allow in vertically polarized light, and now this pair of glasses down here are only going to let in horizontally polarized light, you get a nice little crosshatch looking pattern where one lens blocks vertically polarized light, the other lens blocks horizontally polarized light, and you get absolutely none. What I did is in the store, I popped out one of the lenses, rotated it 90 degrees above the other one, looked at the guy who was trying to sell them to me, and I had to explain to him these aren't polarized. The optometrist came out and said, yeah, they were mislabeled. They weren't supposed to be in that section. He'd give me a discount because they weren't really polarized lenses. Whatever. I got a pair of glasses super cheap. But the point is that's how it's able to block a lot of that glare and cut down on that light. So I believe that was the end of 16.2. So all you're going to need to know is the definition of polarization. You're going to need to know the definitions for those two terms in terms of shadows. I will put the application question about the moon and why the moon sometimes looks orange or red, because that's a really good one to know. And then I believe that was it. The rest of it will be color addition, color subtraction, and why things look the way that they do. So that's going to wrap it up for this year of physics. Again, it's a real bummer that we couldn't have done all of this together. I'm sorry for that, but I hope that at the very least you're able to get something out of all of this in terms of general knowledge to just be a little bit more informed, a little bit more educated. That's obviously the goal. So if you have questions, if you have concerns, as always, email me. I will post answer keys to the worksheets that are going to be coming out today. Sorry, today is, what day is it? I don't even know. Um, the 11th. So I'll have everything uploaded for you guys by the end of the day on today, May 11th, and that will be everything for the next 2 weeks. That's how we're going to end up wrapping the year. So sorry, this was 45 minutes long. This is the longest one that we've done because this is the end. It's good for 2 weeks. So wish you guys the best. I'll miss you. Can't wait to see you in the fall. Let me know if you have any questions or concerns. Please don't hesitate to reach out. See you around.